Hello and welcome to the first of our series of podcasts. We're here with Standstill and Hot Mix Parts. My name is Steve Elam. Happy to be joined with Jack Shaney, who's a chemical engineer of our Louisville Dryer sister company. And today we're going to attempt to delve into some of the details of an air system on an asphalt plant. We'll be talking back and forth some on some of the industrial sides and how they parallel and how they apply to us. But for the most part, our interest is trying to create a forum which we can provide the asphalt industry, the hot mix industry, with some valuable feedback relating to air, how it can help our efficiency, improve our production, solve some problems. And we'll be looking to you to comment on what we're doing. We have the benefit of our hot mix universities where we do just that. We poll and we survey and ask, besides what we've presented, what would you like to hear? What do you need to hear? What didn't make sense? We'll be asking for you to comment throughout the session and certainly at the end of this so we can continue to make this better and be something that is helpful to you and to our industry. Again, Jack is a chemical engineer, but with a lot of specialty in the air system side. He goes out and does studies on site all the time. And Jack, you can mention a little bit of some of the things you have to do with relationship to the air systems out there on the process.
Yeah, and that's one thing that a lot of people either don't have a good grasp on or they don't really think about too much sometimes is the air systems. And that's one of the first things we'll look at when we get out there is I've gone out and done evaluations where you'll take a pitot tube out and you'll actually put it in a duct and measure air volume for a fan. Some people think, what is the ISIGMIB? If something is good, more is better. And that's not always the case with fans. You can oversize them, you can undersize them. And so that's one thing we look at initially. And we'll do material and energy balances on the whole system. We'll look at, okay, how much material are you feeding? What's the moisture in it? How much water vapor is that creating? And with that sort of.
And while we're there, let's go ahead and stop. I mean, this is a great. No. This is a great point to stop on an important. Some of the descriptions or nomenclature we speak of. Some of our folks in the field may or may not know some of them, and I'd like to go on and talk about a heat balance. Talk about what is your plant supposed to do, and that's some of the biggest questions where we get started. Is our plant isn't working right, so here we start and. The whys. How does it get there? Is it, the just rudimentary things of are we getting proper burns to dry and heat the process? What are the aggregates? What are we even trying to do? So let's talk about what a heat balance is, and this applies to whether it's the process side or the asphalt plants. This is the right way to go about looking at a problem rather than to dive into the minutia. Always making sure we're looking at the broad spectrum of what we can do. So you can explain a little bit of what is a heat balance?
Okay, real simply, like a heat balance. So basically you need a certain amount of energy to do the work. A lot of people will talk in terms of, well, we're not getting throughput we need. We can't get, 200 tons like we used to. We're only getting 175 tons. Why can't we just push more through? Well, it's more than just physically moving material through. The heat balance is basically how much work you're trying to do. And on the drying side, sometimes it's a little more straightforward and there's some other complications too, but essentially you say, how much water's in the material? How dry are we trying to get it? How hot are we trying to heat the material up to? So there's so much energy required to heat the material up, and there's so much energy required to boil that water off and out of the material. And then you're going to have so much stack loss, after that. And there's other factors that come into play. If you've got wrap or you do other things, there's other materials that have moisture in them too. That require energy to do the work. So what we do when we come out and look at a system, we would say, okay, what is your throughput? How much material are you trying to feed into this dryer, into the asphalt dryer? How much moisture is in the rock that you're putting in, or the sand, or the constituents? So how much water vapor is that going to generate? How much energy do we need to evaporate that? How much energy do we need to heat the material up sufficiently for all the constituents to mix well? And that's what it's composed of. It's not just pushing more through. It's not just this or that. And specifically in other industries too, when you've got big piles that sit outside all the time and they're not covered, and you've got rain can come through and things like that. Things like moisture matter. It's not just hey, we can't run the same tonnage we have. Your moisture might be 3% today because it's been dry for a while, and then the sand that's sitting out in a pile, in a week or two, you just had a big rainstorm come through, and it might be 10%. And that is a huge difference in energy requirements.
And we'll keep coming back to
Yeah.
this, and what Jack is certainly defining here that overlays onto our asphalt process, which we use routinely, is so often we have set in our minds that an X diameter dryer at X length must have a burner big enough or not, and that it's not doing the production it needs. And literally, I would, while I haven't counted, I would venture to guess it may have been 1,000 times, certainly hundreds and hundreds of the calls that we receive of can't have production, we don't have production, our burner's not big enough. And that has only been the case in 2 to 3 cases, and 2 of those were when burners were changed out. So very uncommon or unlikely scenario. And these are some of the things we're going to talk about of the but whys. How do we get there? And what Jack is saying that we imply or employ onto our diagnoses of some of the plants are looking at what you're trying to accomplish versus what you are accomplishing. And we begin with, if wherever possible, while we're gathering or gleaning this information, is looking and putting together what are the capacities of this system, whether it's needed or not. What is the capacity of the system with the fuels being used, et cetera? And then that provides a baseline. Certainly if we said we wanted to run 600 tons an hour with a 5-foot dryer, I think most everyone in the industry would say, not going to happen. And that's true. But when we start getting closer to things that seems like it should be running, et cetera, we'll begin to get into this. So this heat balance with both the energy, we intend to drive towards the air systems here. Right. But if we don't have air, we obviously can't do this. And I'll start with this and let Jack dig into some of the details. But I always just like to mention and make the blunt point of how much air do you need for an asphalt plant to do its job. And we can go down all types of bunny trails of how much is needed and get into a lot of specifics. And we do need to potentially. But the simplest way is to think that we need enough air to support combustion, evacuate the gases, and consider the real world asphalt plant that it's not a hermetically sealed device. It isn't perfect. We're going to have energy losses. We're going to have some air leakages. Some becomes very operative as we start to talk more about what is allowable versus what exists, and look at how we need to get to where we go. And this is really for any plant, any type, whether it's a batch, drum, counterflow drum, whatever that may be. So getting into the air systems a little bit and kind of the fuel ratios, why are we, in today's world, there's very few wet washes out there. So we're largely and mostly going to be discussing baghouse scenarios and situations or applications. However, we can dabble. Most of the conceptual information here does relate to just the energy process and the air being pulled through the system to support combustion. However, we'll get into how that air has to be processed and the major impacts it can have. So Jack, if you would, a little bit of why do we need any specific volume of air through a system?
Well, and I'll say too, I mean, you basically sort of said it, but rule of thumbs are great. It's good to be able to say, hey, drum's this big, we're running this much through it. This is about what the air volume should be and all that. And those are very helpful and those are very good. But when you get into specific cases and you've got leaks and different, you're not the standard necessarily with all the changes, whether it's blue smoke systems or whatever else. Rules of thumb will get you close, and maybe that's right where you're at. But the purpose of measuring the airflow is you know exactly what you're doing, like whether you've got higher moisture than normal, whether you're running a little hotter than another plant, whether you're I don't know, things like that. There's other things to take case, whether you've got a bunch of leaks, whether that's like at your discharge hood or in your duct or your cyclone, maybe somebody can't, hasn't been keeping up with maintenance like they should, or really been walking the system down, and you think, oh man, I don't know what's going on, or Or another one, if your fan's physically not pulling as much air as it used to, like say you've had a couple bags fall out, or somebody hasn't been checking that, or you've been checking it, but you've just got a hole somewhere, and that sand eats out your fan wheel, and you're still running 55, 60 hertz, or you keep cranking the fan up, and you just can't get where you used to get. It's a way to come in and say, yep, without having to necessarily take the fan totally apart, you can take an air measurement and say, yep, this fan's moving a lot less air than it should be, and it's just ways to determine that.
We're gonna delve into that, because that's one of my favorite things is to bring up to people. It's kind of like if I'm at a plant site and people aren't doing the production they are, or there's some nonsensical things potentially going on that don't initially add up. One of the very first places I go is just drilling a hole in prior to the fan.
Right.
And we'll take negative pressure readings. So we're going to get into that. We'll actually be showing you some visuals here overlapping in a little while, where we provide a data sheet. And it really is, when you walk into the doctor, if you go into the ER and you may not be dying, but you need some help, you hope they just don't start cutting you open for open heart. They're going to check what your pulse is. They're going to check your blood pressure. They're going to take a lot of vitals. And we want to know that information so we're going down the right path and we have baselines. But one thing I would like to get to back and steering it towards the asphalt plants again, just because the process side is so all-encompassing. The dryer sizes can be so radically different, from very small pilot dryers you do in testing, and we'll get into that in a moment, but all the way up into whether they're 17.5 foot in diameter, 2 inches thick, 130 feet long, made of various types of stainless steel.
Right.
All these types of different processes. But I think one thing that we'd be interested, that might be impressive and it's interesting, but one thing that applies to us on the asphalt side is that when we're trying to create quality hot mix, unless we're making cold mix, obviously warm mix is going to come into play here, or reduced temperatures. But by and large, if we keep in our minds that we are trying to take aggregate materials of varying sizes to make a mixture, in other words, what is the product we're trying to create? In the end, once it's dried, and that becomes very operative, once it's thoroughly dried, we try to blend it with a binder. And some nominal numbers at 5 or 6% of binder or liquid AC, once ideally this process is nearly done. We'll get into recycle, but drying this material thoroughly and heating it to a predetermined temperature or target, 300 degrees Fahrenheit is a common. It may be more than that in given areas with polymer mixes, etc. But we're trying to, in all practical terms, thoroughly dry our aggregate systems, our aggregate product out there in our systems, so that we can paint or coat these materials. In the process side, it sometimes becomes very unique. In other words, we also delve into pre-bagged concrete as an example. And simply speaking, it's very similar mixture where we have some fines, intermediate and larger size aggregates with some cement, and we want it thoroughly dried, so therefore it doesn't harden up with the cement in the process. However, in a perfect scenario, if we can make that as cool as possible, so if they're putting it in paper bags, it doesn't combust. Right. It can actually, if we try to dry it too much, get it too hot, it actually burns the bags prior to or after they put it into the bags. So there's a very different outcome. Temperature is as low as possible. How can we get the job or work done? In our asphalt process, we do have target temperatures we want to achieve, whether it's warm mix, whether it's hot mix, whether it might be in Arizona or California where we have some higher temperature polymer grades, and really all across the country. But Jack, you could speak to sometimes you'll be reducing a given seed or something from 13% moisture or 20% moisture down to 7, or if you could elaborate, please.
Yeah. So we we build dryers, and they all do very similar things. You put wet material on one end, dry material out the other, and in a nutshell, in like the crudest nutshell you can think of. but there's so many different energies, there's so many different processes and products I'd never even heard of, and there's this niche process where they're making some $1 million industry that I never heard of to go into this other product that I never heard of, and that's why I like it. But yeah, your specs of what you're shooting for are all over the place. You go from, hey, we've got the distiller's dried grain where we're trying to come in at 60% moisture, and we're taking it down to 10, but because of that we have to have a recycle stream where we take some of the product back around and blend it with the feed so it'll actually handle through the dryer. We've got some stuff it's simple.
I can translate that. That's
Oh, sorry.
No, I'm being a bit facetious here, but for those out there, just kind of a bit of interesting thing. Louisville Dryer many years ago came from basically distiller's grain. So what is that? Well, Kentucky is known for bourbon, for where we happen to be located. And what's the process? Is there any problem with putting a direct fired onto compressed corn and a lot of other goods after it's wasted?
You can do it. So there's a lot of handling on the front end. After they make their alcohol, you're basically left with what they'll call it's either slop or whole stillage, is a less crude term, but and it's like 95% water. They'll centrifuge it, split it off. Part of it goes to some evaporators to concentrate it down. And the wet cake is what comes off the other side of the centrifuge. And sometimes the syrup will get brought back to the wet cake. Sometimes just the wet cake goes to the dryer. Sorry, I started talking and lost the question already. I was
no,
going
we're
too
just.
far back.
I think the interesting part that some of us may find out.
Direct heat.
It's just about the direct heat. We are trying to take a waste product.
Yeah.
And this started back in the early 1900s from making bourbon.
Yeah.
And how can we utilize that? Animal feed is a huge opportunity there. However, it's not in a form we need. It needs to dry, but simply drying it isn't as simple as it sounds.
And the reason dryers need it anyways, there's this whole stillage is so wet. I mean, it might last a week maybe before it's rotten. So sometimes they can give it away to farmers if the tonnage isn't real high, but usually you have to dry it and then you get a year shelf life plus. And you can do direct fire to direct heat dryers. I mean, direct fire would probably be an absolute no-no because we live in the world of organics instead of just rock, sand, gravel, and things like that. Organics, you've got to be real careful because you will more than likely have fires in a direct heat dryer drying distiller's dry grains. Maybe you get lucky and they only happen occasionally, but they are probably going to happen.
Going in, if we're going to do X amount of work, as you said, you do a heat balance and say that we have 300 tons per hour and we may need 50,000 CFM or with wetter moisture 60,000, whatever we're needing. These baselines have long been determined through real world processes over a long period of time. Many previous manufacturers, everyone's done testing, but in the end, we don't have a magic parcel of air, a magic bit of fuel that does things. We just have the efficiency. We can take that energy we're creating from there. Right. But since we're going to produce a certain amount of BTUs as efficiently as possible, we need some air. How do we get this air? What are we doing on our burners? And
maybe I'll compare direct fire to direct heat to try to help explain how this sort of lays out. So as Steve mentioned, direct fire dryers are more efficient because you've got the burner like mounted to the feed hood or right there at the dryer, and so you've got some radiant heat and all that's right there at the material. And what you're actually doing is you're heating the air, and depending how hot it is, that air holds so many BTUs per pound of air. So when we get into direct heat dryers, when that inlet temperature is lower, your BTU for every pound of air is a lot lower. So, just assume, you've got a volume of air this big and it holds so much heat to it. Like let's say it's, 200 BTUs for every pound of air. And you're pretty hot. If you have to go cooler, that means there's less energy in the air available to then put into the material. So if you're doing, 200, if you're doing whatever throughput through your dryer with this much air and then you cut your temperature way down, you're going to need 2, 3, 4, 10 times as much airflow, and your air volumes and your velocities go way up. So that's why, like I said, direct firing into it, you're coming as hot as possible. You need a minimum amount of air to carry that heat into the material. And that's what dictates, from the start. You say, okay, we need so many million BTUs to do this work, to actually get the heat into the material, and then based on that and how many BTUs per pound of air you have, you say, okay, from this, I know how much more how many BTUs I need. I know how many BTUs I can cram into a pound of air. So this is how much airflow I need. And that's then how you can, theoretically, at least on paper, size a dryer. And it's remarkably close. For calculations, it is very, very close. But yeah, in a nutshell, that's it.
We want to get started with the best case scenario of if we want to have an outcome of 300-degree mix and we have 5% moisture in the virgin aggregate and 3% in the recycle, we're going to either have an output of 300 degrees Fahrenheit or 320, or with cooler temperatures to help with emissions, we might want 270 with warm mix or chemical additives, foaming. Once we determine this, we therefore set up the size of the equipment.
Yeah.
If we're sizing new equipment, how big should the baghouse be? It's a question I've been asked so many times, and my canned answer is typically, how big of a baghouse or how large of an air system do we need? My answer is bigger's better, until you get really financially stupid or we have to start insulating the baghouse because of dew point problems.
Eventually you'll get there. It just takes, if you get down maybe like a 2-to-1 or something, you get to be so massive you can't keep the thing hot, then
We'll talk about those. But so do we have a big enough air system? In other words, if we start with a statement, we need enough air to support combustion and a little bit extra, whatever that amount is for the desired tonnage we want, if we don't have that, or if we have the equipment that by specification says it should do this work, but it's not, we can talk a little bit about how we get there, but and start troubleshooting to find out. But if we do go back again, elementary, starting at the burner, whether we're using natural gas, waste oils, number 2 fuel, a lot of LNG and so forth now being introduced to the industries for cleaner emissions. What are we doing with this baghouse system? How do we regulate or control? Do we just push? I said a bigger baghouse is better. Do we just push more air and everything's good?
Right. I mean, that's people end up doing that sometimes and just put a bigger fan or push more air. But if so, undersizing a fan, everybody can see, hey, I need more air, I don't have it. Oversizing can be an issue too, because you're either sort of wasting horsepower and pulling more air than you need to do the work. So either you're either pulling in more ambient air and you're exhausting a little cooler, which could lead to condensation problems in your duct or baghouse. Or you get to a point.
If we're cooling and quenching, if we're pulling in more air than we need and cooling and quenching the flame, we're also creating more volume.
You got more
translating to velocity and dust carryout. But is that efficient? I mean, that's not a good plan, is it?
It's definitely not efficient. And then on top of that, you can make a fan so large that it will not run properly. And that's a whole nother thing with fan curves where, there's a spot where they like to run. And if, like I said, you make it so sufficiently large that you can't turn it down, they can go into stalls and do some funny things if they're not sized right.
Very great point. And oftentimes, we simply think if we have a gearbox or something, bigger must be better so it won't break. And some of those fundamental rules might be correct within reason.
Right.
When we start talking about fans and burners, and we have a determined level of production we're trying to achieve and a determined range of production for which we wish to operate in, bigger is not better.
Right. And that's
smaller becomes very simple because it won't do the work.
Range is a big
bigger
thing.
is not better.
Because if you run it 300 tons normally, and then occasionally well, some days we're going to run down 50 or 100, and maybe that's not super common. But if you need a big turn down, then you've got to check your burner can do it, make sure it's not so large that it can barely get to it. Or I've been at plants before. I think it's just a sand dryer, but they had they found a drum in the weeds and a burner in the weeds, just something wherever, had it forever, and they were running like 50 tons an hour on a 5-foot dryer with no water in it. So I think the burner had to turn all the way down, and then we had to take a bunch of take a bunch of seals off to suck in a bunch of extra air so that they didn't overtemp their baghouse and burn it up. When you're calculating airflow, we would take a pitot tube measurement, and we can show one or whatever. But it basically it's just like a tube, and you can make them. You put them in the duct, and it measures the pressure in the duct. So you've got so what it's actually measuring is it's comparing. There's total pressure, which is composed of velocity pressure, which is the force of the air coming through the duct, the force of the air traveling through it, and static pressure.
Real quick, I told you I'm the analogy nut or the
Yeah.
little real world kid. For anyone who's been on an airplane, I hope most of us have, if when you're boarding, you look off to the left and you wave to the pilot if they're in there, you'll notice sometimes a little L-shaped device that comes out with a point on it, or a couple of them. Often it says, don't touch these because they may be heated so they don't freeze up. Um, those are pitot tubes, right?
That is a
They're
pitot tube.
measuring airspeed. So what they're doing is that
Yep.
velocity pressure as the airplane goes faster, pushing pressure.
Yeah.
For those folks out there that might be bass fishermen or other things, and you have a relatively accurate speedometer, it's sort of the same thing down under your boat, pushing pressure in a tube, giving pressure back to a meter that says you're going X miles an hour. Jack takes this to another level when we're measuring this, but it's very important.
Yeah. And essentially, you want to measure velocity pressure, but because when you go to measure velocity pressure, you're also measuring the static with it, you get a higher value than what it should be. So with a pitot tube, it's set up so that you're measuring the static separately from the total pressure, and then you subtract and basically take a differential, and that gives you your velocity pressure. And there's equations that exist that you can plug it into a formula, and it spits out, oh, if your velocity pressure is this is what your velocity is. And if you know the area of the duct, then so if you know velocity pressure, it gives you a velocity which is in feet per minute. Then if you know an area, which is square feet, then you can get to your volume, which is cubic feet a minute.
Great news is no test.
Yeah, no test after this. You can rewind if you want, but
these calculations should be done for, we have set velocities within the asphalt plants.
Yeah.
For example, clean ductwork we might call after a primary collector versus dirty air ductwork going into a primary collector. We look for different velocities so that we both can have the proper throughput with a reasonable resistance, and that's what we're going to get into a little bit next. And keep suspended all of our materials, our fines.
Normally, if something makes it in the duct, you want it to go to the baghouse. If it's going to get there, you want to keep on going. You don't want stuff settling out, and then you got a duct half full of material that's got all this extra weight in it, or
then thus creating restrictions.
Right.
And we can at some point even get into long horizontal runs are typically taboo, where we can create some laminar flows and get sediment, and then we create restrictions, etc. And so we start creating problems. So these are some of the fundamental 101 type of things that we want to look at. In other words, what do we mean by draft that Jack's talking about? He mentioned the fan is the highest level of suction. That means that's the working device its goal is to pull this airflow through the system. Gets a little more complicated as we have total air burners and so forth, which assist and provide positive pressure back at the burner. But what we're referring to is at the burner, what is the negative pressure? What is that slight vacuum? Because if we don't have negative pressure there, what happens around that area?
You're uncontrolled, which it's in a nutshell. You may be drying, you may not be drying, but you are, if you don't have a draft and you're not pulling that heat from the burner through the sand or through the asphalt or through whatever you've got in your dryer, then you might be hitting production, you might not be, but you're at least wasting some energy because you get blowback. And I don't know if we've had customers that have lost draft or not had good control, and you'll melt like ignition wires, you'll melt anything that's back there that's open that can see any of that. The flame will kick back, it'll come out the seals. Potentially, I mean, it can cause problems, especially when you've got a long flame or a big burner on there. It can cause some problems.
And that's the typical thing we see. And most of us do, either through intuition or training, understand that we may, and certainly in days of old, before the total air burners, where we had open fired and simply put, you could physically see the flame. And in that case, the dampering system, because there weren't many or any VFD systems operating, managing the quantity of airflow, we relied on dampers on the fans. We would turn our dampers down or throttle or regulate the airflow up until the point Jack mentions where it
Stop the
terminology is
puffing.
puff backs.
Yeah.
And then we would open it a bit more. And at that very point, because when it puffs back, it should go to, in effect, zero, because we don't have a draft or negative pressure. So we'll look for something greater than that. And more, again, is not better. More would translate to, for example, in an open fired burner, that we're pulling more excess air than we need. Going back to that first fundamental rule, how much air do we need? Enough to support combustion and a little extra. Kind of keep etching that in your mind, that once we create that airflow, and if our burner, big if, is tuned properly and can manage its air to fuel ratio, we now have the air to support the combustion, so we can create the energy that we're going to then try to gather a great deal of and put into our product. So these are those fundamentals. We have to have that pressure there. And I know, having been out in the field with Jack and having the good fortune and pleasure to work with Jack on some systems, that, we go around on the plant and we have to effectively troubleshoot an entire system, don't we?
Yeah, and sometimes it get a little sticky where you basically got to start from scratch. And if it's an old enough system, you almost can't assume anything's okay. You sort of got to double check everything, because if you like a greenfield installation or something brand new, you've got some major things that can be wired wrong or screwed up. But yeah, if you get into an old plant, you sort of got to walk the whole thing down and say, okay, is the burner working okay? Is this thing set up properly? Is it the right size? Is the fan the right size? Is this what kind of throughput do you have? Has there been any changes recently? Has a bunch of ductwork been swapped out? And you sort of just got to go through from scratch from the start, and just you can't make any or too many assumptions, because it always seems to turn out. Sometimes you get into some big issue where it's like, man, just not pulling what we want, and then come to find out the fan wheels wore to pieces, and it's something that's not, yeah, not something you'd
And
see on
something that's common, going back to fan, as we jump around a bit, but this is the real world. We're trying to give you the feedback that applies to our asphalt plant operations. We all know we are supposed to have our filter media in our bag houses
Right.
Of a proper consistency and working well, without holes, without seal leaks, etc. And sometimes that's not the case. So, and let's just say often that's not the case. So we have particulate flowing through what is meant to be a clean air side.
Right.
And it could have been before someone acquired that plant, the previous operator wasn't doing their work. But sometime down the road, now we're having problems where we can't get airflow. We often have to put inlet cones, which looks like the end of a trumpet, into fans, from where that's a thin piece of extruded metal that's not some thick abrasion resistant material that was put there to be able to survive that. There may be chemical degradation there from waste oils and moisture, from sulfuric acid creation from dew point issues, where it'll erode the metal. And those things, going back to taking the pulse as you go in the ER and taking these basic measurements, that's what we can do when we look at the fans, when we determine that there is a preset range we're looking for. If this air pump, what we call a fan, is not capable of the suction pressure, the negative pressure we need, we're not going to get the work, at least at full capacity, we are expecting from that. Looking to make sure these systems work properly, but going through this template we talked about as we measure systems, what are some things? I know we looked at, you and I, at a system in the north a couple of years ago where the plant didn't seem to be performing, and I know we spent some time around a knockout box. What did that entail? Did we just take some ladders and look around? This is a big facility. What did we?
I mean, it was definitely a pitot tube measurement, and this was, yeah, I can't remember. high on the lift we got 100 foot in the air, whatever, to get up to ductwork. But essentially, one big thing to do is to take static pressures. Just put a hole in the duct, put a tube in, measure the pressure at that single point. Not a pitot tube, not a flow, but just measure the pressure at points, and you can measure before and after equipment. And if anybody's familiar with like Baghouse differentials, that's essentially how it works. You'll have a reading at the clean side or dirty side and a reading on the clean side. And the difference is the pressure drop across the Baghouse. If you've got all these filters, you're going to have a real high pressure drop. You can go through, and if you do a baseline of that, and then over time you start having problems, you can go back and remeasure those and say, okay, what are we now? Has something drastically changed, or and that's one good way to get a baseline and to start a troubleshooting, especially for an air system.
And I think I'll chat on a couple of real quick real world scenarios, one of which is occurring as we are talking here, where a customer changed out a cyclone, and the issue was production went down greatly. They had built a homemade local, with best of intentions, knockout box. It was a little overly simplistic. Now, we're not convinced that's the entire problem, but for certain, it was less efficient.
Finding a single smoking gun's pretty difficult. It's a lot. It's, sometimes you get lucky and you show up and say, oh, this is exactly the problem. That's it. We got it. We're done. But a lot of times it's a combination of lots of little stuff, or little this, and this is causing that, and things like that. So
if we walk up to a plant today and the first thing they said is 5 minutes, you get to go look and see what we can't run production. Why is it not doing that? I think the first place I run is to go poke a hole in the front of the fan, stick that, if they're running full speed but can't achieve production,
right,
we want to see that the fan, which may be just fine
right,
and actually pulling the desired static pressure, but clearly we're not getting it through the system. So our air pump is actually okay. Let's start working and finding out
right.
where these other places are.
And you can measure volume at lower temperatures. Like, you could potentially put your burner on low fire and try to and get do a small correction, so you don't have to worry about water vapor and some stuff. But it's also not with the system running and all the pressures and everything exactly where they need to be. But so but then also you got to be down to do that. You can't just so if you've got to run, you'd have to do it after hours or do something else, and a lot of people can't necessarily do that. Or
These are important things though, because
right,
sometimes we don't get that luxury. People have to run mix.
right,
And we're there
exactly.
to help them. And the ways Jack's talking about is that we can do some workarounds on these things. You mentioned earlier something that's important. Oftentimes we're damaging equipment when we don't have this
Yes,
balance
you
of
can definitely do
air
that.
and fuel. When we have this lazy flame scenario, in the case of a total air burner, where we're supplying a lot of the primary air required to at least initiate a large volume of combustion, if we're not drawing that through, we can have a very lazy flame, which can, as you said, burn up leads, damage radiantly the equipment in the
Right.
back. And that is a common scenario, oftentimes in the combustion flighting, doing significant damage.
Well, and even like emission stuff, not to speak like exact absolute specifics, but usually when they're tuned assuming so much airflow in and around the burner, so much coming through it, and that's balanced so that you get, sort of emissions you're looking for per your permit. And if once you start messing with that, you might fall outside that, where you might not be combusting as efficiently, you're generating a bunch of CO, or you might, any number of things depending. So
And that's usually the case, that it
right,
does create a great
it's
imbalance.
starving and it's looking for air and can't get it.
Exactly. And either we're not getting the numbers we want to be reading, we're not getting the metrics, the um, things we need for efficiency, and or we can't simply get production because of these
Yeah.
types of things. As we're wrapping up, what we'd like to do is ask you to make comments below. We are learning in this process. While we're utilizing the experience from Hot Mix University, we want to actively start to seek out what you want to hear and try to address that. There's a lot that's come from our industrial partner in the process side here, but we want to continue to grow this and make it better for what you want. Please comment. We'll be looking to seek your input and address it and apply it as we can. So thanks again, Jack.
Yeah, no problem.